Okay, so this is what we covered in class today, the 14th. The packet, you were given functions for section 3-4, number 61 to 64. Alright, so far, we know behavior of a function as far as where it's increasing and decreasing, and we have determined concavity of a function. So when a function changes direction from increasing to decreasing, that occurs at a relative maximum. Where a function switches from decreasing to increasing, that occurs at a relative minimum. A change in concavity would be a point of inflection on the graph of the function. Alright, so intervals where a function would switch from increasing to decreasing. If a function is increasing, we know its first derivative is positive. If a function is decreasing, we know its first derivative is negative, and it's, again, back to positive. Yesterday, the second discussion question in class, we talked about what concavity tells us about the graph of the derivative. So on an interval where a function is concave up, the derivative is increasing. On an interval where the function is concave down, the derivative is decreasing and then increasing again. Okay, so today we're going to be sketching the graphs of f prime and f double prime. So where a function switches from positive to negative or negative to positive, that occurs at a 0. A change in direction on any graph occurs at a relative extrema. So we have two bits of information about the graph of the derivative. We'll know when it's above and below the x-axis, and we'll know its behavior as far as increasing or decreasing. Now for the second derivative, the interval where a function is concave up, we know that's where the second derivative is positive. Where a function is concave down, second derivative is negative, and then it would switch to positive again. So on the graph of the second derivative, the points of inflection become the zeros of the graph of the second derivative. Okay, so let's try to put all this together. So again, I have packets of these graphs, but here's my function f. So for each one, we're going to determine the behavior of the function, increasing and decreasing, and concavity. So my function is strictly increasing, and my function has no concavity. So again, the easiest way for me to describe concavity would be an upward or downward facing parabola. Okay, so if my function is strictly increasing, my derivative is going to be strictly positive. If my function has no concavity, my derivative is going to be constant. There's going to be no change in direction. And then lastly, if my function has no concavity, my second derivative has a value of 0. Alright, so let's start with graphing the second derivative. If I ask you to graph the line f of the line y is equal to 0, that would just be a horizontal line through the x-axis. So my second derivative is exactly that. A horizontal line through 0, so it would be a horizontal line on the x-axis. For my first derivative is strictly positive, which just means it has to be above the x-axis. Now what's the first derivative? It's the slope of the tangent lines. So if I look at this graph and I were to ask you what's the slope at every single line tangent to the function, it would just be 1. So the graph of my first derivative would be a horizontal line through 1. Okay, so for this function, f of x switches from decreasing to increasing at 1, and my function is strictly concave up. Alright, so that tells me about the graph of the derivative I'm going to have a 0 at 1, and the derivative will switch from below the x-axis to above. If my function is strictly concave up, then my first derivative will strictly increase. And then lastly, if my function is concave up, that tells me that my second derivative will be strictly positive. Again, meaning just above the x-axis. Alright, so let's start with the first derivative. I have a 0 at 1 on the graph of the first derivative, and the graph is going to change from below the x-axis to above the x-axis. So my graph of f prime is just an increasing line, which verifies what we determined from the concavity, that my first derivative is strictly increasing. Now for the second derivative, we know that the second derivative is positive, which means it would be above the x-axis. And looking at the first derivative, if we were to look at the slope of the lines tangent to f prime, they're constant. So my second derivative would just be a horizontal line above the x-axis. Okay, our next one, we have a few changes here. So f of x starts out increasing, then it decreases, then it increases. And my function has one change in concavity, so concave down to concave up. So changes in direction occur here. We call that -1/4 in class, and here, so we'll call that 1.5. And then a change in concavity, we'll call that 1/2. All right, it's without actually finding the derivative, we don't know what the x value is. Okay, so the first derivative is going to switch from positive to negative at -1/4, and then from negative to positive at 3/2. And the first derivative is going to change direction from decreasing to increasing at 1/2. Alright, so I'll have a relative, I'll have zeros at -1/4 and 1.5, and I'll have a relative minimum at 1/2. Now we don't know the y value of where the relative minimum occurs. The only thing I know about it, if I look at x is equal to 1/2, it has to be in the negative region. Okay, so 1/2 is somewhere between -1/4 and 1.5. So I'm just going to put it here. So now putting these two pieces of information together, I know that my function has to decrease then increase, and this tells me the graph will be above the x-axis to below the x-axis to above. So once I have my points in place, I can just sort of look at connecting those points. All of my information is verified. Now for the second derivative, at 1/2, my second derivative is going to switch from below the x-axis to above the x-axis. So at 1/2, the point of inflection on the function becomes a relative extrema on the derivative, which becomes a 0 on the second derivative. So notice how all of those are in line. Now one question that is asked, well, what about the behavior of the second derivative as far as increasing or decreasing? So to answer that question, we can look at the concavity of f prime. So f prime is strictly concave up. It's a parabola facing upward, which tells me my second derivative is going to strictly increase. So putting these two pieces of information together, I'm going to have a line that switches from below the x-axis to above, and therefore it's strictly increasing. Alright, last one. So f of x, my function switches from increasing to decreasing at 2. and my function is concave up to the left of 2 and also concave up to the right of 2. So I need to make sure I put 2 on the number line because they are 2 is a discontinuity. Alright, what does that tell me about my derivative? My derivative is positive and then negative, but my derivative is strictly increasing because the function is concave up on the entire interval. So remember what positive and negative means, just above the x-axis and below the x-axis. So I need a function that's above the x-axis and increasing the whole time. So above the x-axis and increasing. And then to the right of 2, I need a function that's below the x-axis and increasing as well. So if I extend our asymptote, below the x-axis but increasing. So that's what my graph of f prime would look like. Now for the second derivative, f double prime of x is strictly positive, meaning the second derivative will be strictly above the x-axis. But now this is where the concavity of f prime will help us with the shape of, or the direction of f double prime. So to the left of 2, my derivative is concave up. To the right of 2, my derivative is concave down. So that tells me my second derivative switches from decreasing to increasing to decreasing. So to graph the second derivative, putting these two pieces of information together, the graph has to be strictly above the x-axis. I'm going to increase above the x-axis, and then my second derivative is going to decrease above the x-axis. So my second derivative is in the same spot as my original function. So your homework, and there's a packet of this, it's on Edmodo. Oops. It's page 216, numbers 61 to 64. And you're given the derivative function, and you're asked to sketch the original and the second derivative.